Oh, hey, look, we've got some more people joining the dance party. Awesome. Welcome, guys. We're just rocking out. It's me, Marisa, with the museum, here with Gavin and Graham, the Geology Gents. Hey, guys.
Marisa.
So, this has been really fun. But gosh, we've been dancing for just what feels like hours. I'm getting a little tired. You guys want me to take a break? Yeah? Okay. All right. Gosh, that was invigorating. I kind of want to keep rocking out. So maybe we can transition into the Rockin' pop-up. What do you think?
Sounds great.
Let's do it. Okay, so everyone at home who has just joined us for our dance party turned Rockin' pop-up, thanks for being here. And let us know that you're here and that you are rocking out with us by maybe what we thought would be fun is if you could think of any rock puns that are specifically related to like rock stars, artists, bands, songs. So if you can think of any like names of songs, names of bands that have like geologic tie-ins, put them in the comments so that we know that you're here. I've got a couple in mind, but I'm not going to spoil them. So we'll see if you can come up with anything good. And Gavin and Graham, what's on the menu for today?
So the menu for today is the building blocks of rocks. I can pop my screen up here.
That's got a ring.
Okay, sure. Yeah, let's just dive right on into it.
Great. All right. So as promised, we mentioned this last time, and I've seen the Instagram post. We're going to talk about how we put rocks together, and we've got a rhyme that we were all pretty keen on: the building blocks of rocks. So, Gavin, what's in a rock? We've talked about rocks the last couple weeks. I often see a rock and I'm like, that looks like a rock, but is there more to it?
Sure, there's a lot more to it. So rocks are built of smaller things, right? And so what rocks do we have here, Graham? We've got sort of some different ones.
We've got my favorite Santa Cruz outcrop that you spoiled me by letting us spend all last week talking about, the Swift Street outcrop.
Yep.
What else is on here?
We've got the what looks kind of similar, the Monterey Formation right above Swift Street on the right there.
Yeah, another mudstone. And then of course, we aren't just the earth is made of more than just sedimentary rocks, right? There's also some igneous rocks and there's metamorphic rocks. And we talked about those, very briefly a couple weeks ago, but all of them, right? There's something that goes into them to make them rocks. And so we thought we'd just dive right in by, I'm getting booped. By zooming in and thinking about what goes together in a rock. So I think that would be a great time to just make some observations. And so Gavin and I will be peering into this rock, but we hope that you folks out there will also throw in some observations. What do you see? Gavin, what sorts of things can we pull out of this rock by looking at it?
Good question, Graham. So this rock, well, we've spoiled it that this is a rock, first of all. But it's obviously not a pure mixture, right? This isn't like there are components. And Marisa, how do I know that there are components? What do I see here? What do you see?
So when I look at this picture, I notice some different colors. So I see that there's some black. I see that there's some kind of cream colors. It also looks like some, not quite so cream, a little bit more silvery white. Looks a little shinier maybe than some of the other. So I'm seeing different lusters. I'm seeing different colors. And yeah, I'm noticing that it's like speckled. So it doesn't look uniform.
So it's obviously made of not all of the same thing, but different components, right, Graham?
That's right. Yeah. And so this is a rock that hopefully some of you have seen before. Maybe some of you, when you were making your observations, might have noticed where it comes from. This is a surprisingly well-known California rock. This comes from Yosemite. These are the granites that make up this whole big area here. And so, yeah, so this is what they look like from far away. And then we zoom in and we can start to see that they aren't just all one big grayish white mass. There are these bits and pieces to them. And so what are those bits and pieces? these are the building blocks of rocks that we promised today, right, Gavin? And those are our ingredients that we call
minerals. Yes, Graham. So if someone asks you what are rocks made of, the easiest and quickest answer is minerals. Minerals are the ingredients that make rocks. So in the middle here, we have that same picture of our Yosemite granite, and we can now take it apart and look at the pieces. And we can do that by basically using Maurice's observations and maybe yours at home. So as Marisa pointed out, there are these parts of this rock that are clear. They really don't have a color. That's the mineral quartz. And so quartz is oftentimes you find it all over the place. It's a common rock forming mineral. And you oftentimes find it with this sort of like oily luster. It really doesn't have a color a lot of the time. What about the black stuff, Graham?
Oh, that's the black stuff. So the black stuff, it tends to be really shiny. Sometimes it even shows up. It's got such a glint in these rocks that people think it might be, flecks of something like gold or copper or something like that. But often, in these granites, it'll if you catch a good, look at it without it being too flashy, it's this dark brown to black colored, and it's a really flaky mineral. We call that biotite, and it's made out of these these really small sheets. So that's the dark stuff. That silvery stuff is the quartz. And then what else do we have in here?
So I think that this rock looks like cookies and cream.
Yeah, you're making me hungry, Gavin.
That's right. Yeah. The cream, the white stuff, is feldspar. That's another really common rock forming mineral. It doesn't really have as much of an oily luster, and it's white. But Graham, why do different minerals form and where? And can they tell us anything about how the rock formed?
That's such a good point. So, right, these minerals got here somehow. So we've got the ingredients to our recipe, but now we need to bake our metaphorical cake. And so how do we make a granite, Gavin?
This is a really fundamental process in how we make rocks in the Earth's crust. So we start off with deep rocks and we melt them. And so when we melt rocks, we make either lava when it's on the surface of the earth, or magma when it's below the surface of the earth. So these rocks were magma, they were melted, they were under the surface of the earth. And the fact that they were under the surface is really important, because you noticed about this rock all the minerals, and the reason you could see the minerals and they were big enough to see with the naked eye is because they had a really long time, this magma had a really long time to cool. And so the minerals had a long enough time to grow big. If they were lava and they were spewed out onto the surface of the earth, the minerals would cool very fast and they would be small. They wouldn't have enough time to grow and to be seen by the naked eye. But these cooled over thousands, maybe even hundreds of thousands of years below the surface of the earth.
Gavin, I tell this whenever I'm teaching intro geology, I always tell my students that a mineral crystal is like a work of art or a fine wine. It takes time. You need to put lots of time into growing these big, large, beautiful crystals. So that's great. So we basically pump a bunch of magma into a shallow part of the crust. We let it sit there for thousands, 10,000s, 100,000s of years, and voila, granite. We've got a huge, we can have anything from something the size of your fist to something that's tens to hundreds of miles across. In the case of Yosemite, that's part of the Sierran batholith, which is just a geology word for a really, really big piece of rock. What
was that word again? Batholith?
Batholith. That's exactly right. It's like bath, like a bathtub, and then lith for rock, because we'll never miss an opportunity to throw lith into something. All right. Okay, so Gavin, we've baked our Yosemite granite. We've prepared that. So let's spend a little bit more time talking about those building blocks, right? Just as we promised. So we talked about 3 minerals, and is that all there is?
That is not all there is, Graham.
Goodness.
This is actually the reason why I became a geologist and I started to like rocks as a little kid, because minerals come in an amazing variety. I'm talking thousands of minerals, an amazing variety of shapes, sizes, colors, and these are the sorts of things that are their identifying features. So here you've laid out nicely, Graham, a couple of different interesting minerals. There are a few here that are sort of specific and special to California. So oftentimes people ask us about serpentinite. We have the mineral serpentine here. It's a green mineral. It's often fibrous. Graham, you had been talking to me this morning about bonitowite as well. And bonitowite is the state gem of California. And then you can't talk about California minerals without talking about gold. It's what, gets everybody really excited. And so, as you can see, we have three rocks that can minerals.
Oh, careful, Gavin.
We have three minerals. That's right. We have three minerals. All can be found in California, and even in a pretty geographically small area, but they look very different. And it all depends on what's in them and things along those lines. And we'll get into that in a second. But what else do we see here, Graham? I see you put some of our favorite minerals on here.
Oh, Gavin, I couldn't resist. Down there in the corner is my favorite mineral, staurolite. That's one that forms in metamorphic rocks. So we spent a lot of time talking about sedimentary rocks. Today we started talking about igneous rocks. Metamorphic rocks are the ones that don't get quite hot enough to melt, but hot enough that you change all the stuff in them from whatever was there before. So staurolite is what you get when you take a mud and you bury it really, 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 really deep underground and squeeze it and cook it. What about those other two, calcite and fluorite? Gav, those are your favorites and in your wheelhouse.
That's right. Yeah. So Graham mentioned that if you have staurolite, you know that these rocks were metamorphic. And so that's something that's really cool about minerals and why they're so good at identifying features, is that when you see minerals, oftentimes they're a function of the processes that made them. So calcite and fluorite I really like because they're made in hydrothermal environments or areas where you have a lot of water that has been in contact with really hot magma. So it becomes this really, really hot, salty fluid. And those form the minerals calcite and fluorite. Graham, why do you have diamond and anthracite coal up here, though?
Ooh, a great question, Gavin. This is one of those things where when I first learned it, when I was but a wee geologist myself, it really impressed me. So diamonds, I don't think anyone out there is unfamiliar with a diamond, right? We love thinking about diamonds. They're brilliant, they're really clear, just a lovely gemstone. But diamonds are actually made out of the exact same stuff as anthracite coal. Yet these are two different minerals that couldn't look any more different. And so this gives us a really important, insight into, okay, well, we know that minerals make up rocks, but then what makes up minerals? And so how can a diamond and a piece of coal be the same thing? And it all has to do with how those parts go together. And of course, those parts are the elements.
Oh,
Can I jump in really quick too?
Yes.
If you could go back to the previous slide, because this has to do with what you're about to talk about. But we had a question
from
Liz. She's wondering, why is gold on the elemental table, but not all other minerals? And so if we could talk about that at some point. And another question about gold, someone's wondering if you guys have ever found gold, or if you've ever found maybe just like minerals in general. And then I have a question about that staurolite, because have you guys read Harry Potter?
Mm-hmm.
Yeah.
It looks like something got splinched when
oh my goodness,
it's evaporating. That's a weird shape.
It's a very weird shape, and it's characteristic of staurolite. It's called cruciform crystal habit. So it's all about these ways that our elements are being put together in there. If we pop ahead to this slide, I think folks can see my cursor here, right? We've got these stick and ball models here that show the way atoms are put together. Well, the way they do that in staurolite, they'll turn it into this big X-shaped crystal, which I've always thought was pretty neat about it.
Yeah, geologists like to call that twinning as well, if they're like me and they can't remember the word cruciform. But yeah, so twinning, that's a crystal defect, literally the way that the atoms are fitting together. I think Liz's question is a really good one too, because that's something that's always like, kind of interesting. So let's, for a minute, indulge me and we'll go into the actual technical definition of a mineral. Okay, the technical definition of a mineral, I won't dive in too deep, but it's got to be a crystal, and it's got to be the purest crystal form. And so because gold can form a crystal, the element gold can be concentrated enough in an environment, it forms a crystal and it meets the criteria of being a mineral. It's solid, it's inorganic. So you can do that with a single element. You can also do it with a bunch of different elements. All it has to be is a pure chemical formula. It's got to be solid and inorganic, not ever living.
So so in some cases, things like calcite, that's calcium, carbon, and oxygen. Storolite is made up of so many different elements that I don't dare mention any of them here. So gold is one where you just need one element to make it. There's also a couple other ones on here. Diamond and anthracite coal, those are all just the element carbon. So they're actually just like gold, and where you just have one element showing up. And so those would show up on our periodic table right with carbon as well.
Right. Was there another question, Marisa?
There was one more question that
I'll save it for the end.
Okay, great. Okay, so we won't, a lot of folks don't recall chemistry classes fondly, so we won't make you look at the elements for too long. And we'll just go from all these neat, peculiar, fascinating minerals we talked about, but just focus on three really common ones and how they show up in a favorite local rock of ours, the Purissima Formation. Gavin, take us on the tour de minerals of the Purissima.
That's right. So this is a good opportunity for everyone to see a rock through our eyes and to sort of pick it apart by its minerals. So, okay, what do I see in this piece of the Purissima Formation here on the left? Well, there's a bunch of brown stuff and there's a bunch of white stuff. The brown stuff is what geologists call the matrix, because it makes up most of the rock. And so unlike those igneous Yosemite rocks at the beginning of the talk, this brown stuff, you cannot see the minerals in there. So without knowing where this rock was formed, I would not really be able to know exactly what minerals are in there. But I can guess, because I know that the Purissima Formation formed in Santa Cruz 3 to 7 million years ago. It was a beach deposit there. So what are the type of minerals we have on the beach today? It'll probably be the same stuff that'll be in this matrix. And so the things that make up the minerals that make up sand are quartz and feldspar, those really common rock forming minerals. And so the brown stuff in this sample is made up of quartz and feldspar. And this is a good test because oftentimes minerals can be all different types of colors, right? The same minerals, quartz and feldspar, in our Yosemite granites were white and clear. Here they're brown. And that just has to do with some elemental sort of dirtiness that's inside there. This isn't pure quartz and feldspar. It probably has some iron in there. But let's not talk about elements too long, Graham. It's pretty scary.
Yeah. So we've got the sandy matrix in there. There's also some calcite, or a relative of calcite that's a different mineral, but we won't bog you down with those details. All those bits of shells in there, that's made up of that calcite material. It's all calcium carbonate. And so all of those white pieces, they'll fizzle if you put vinegar on them, because they react with acids in a way that the quartz and feldspar don't. And so those are filling up all that space in there. But now there's also more calcite in here, Gavin, other than what we see in those shells. Tell us about that.
So I think the calcite you're referring to, Graham, could be in the matrix as well, right?
That's right.
That's right, because calcite forms in a few different ways in sort of beach and aquatic environments. So calcite also fills the pore spaces in the original sand that formed. So the same calcite that the shells the animals are building their shells out of is also sort of filling the pore spaces in between the quartz and the feldspar.
And it works as a cement to hold the whole thing together.
That's right. Yes.
So we've told you now what some of the minerals in this are, but we're hoping that we can also, have you help you become mineral investigators of your own. So that's what we'll be talking about next week, where Gavin and I will share with you what to look for in a rock. And so IDing minerals and rocks is tricky, but all has to do with getting good at recognizing those minerals. And so we'll make sure we've got enough time to hit some of those questions, Marisa.
Cool. Thanks, guys. So our other question that we had from Mary about minerals was if either of you have ever found just minerals, or no, gold in particular, but I'm also just kind of curious about in general, like finding those larger chunks of just like pure mineral as opposed to them being mixed in the matrix of a rock.
Really good question. So I can start off with the gold. So I've never found gold in the field. I've never gone up to a rock and found gold. It's pretty rare, which is why it's so precious and why it's so sought after. So I've never found it in the field. One time I had some rocks that we were analyzing from Texas in my old lab when I was an undergrad, and I was chemically analyzing them, and we thought we found gold in them. To this day, I think that we found little flecks of gold. I'm talking microscopic flecks of gold. So that was really fun, but I've never actually found it in the field before. What about you, G?
I've never found gold either. And as far as finding big minerals, I only found some really nice, large sort of gemmy minerals once when I visited an old tourmaline mine when I was living in Maine.
In some parts of Yosemite, you can find, bits of feldspar that are so big that you can like pick up just one piece of feldspar, and it's like a hand sample of feldspar if you like find the right part of the outcrop. So
that's pretty
exciting,
cool.
But it's a mineral all its own. So a hand sample size mineral.
Yeah, that's pretty cool.
I have found gold before.
You have?
Oh, showing us up, Marisa.
Yeah, in a creek in Plumas National Forest with like a pan.
So
wow, cool. That is awesome. Yeah, I've never gone panning, but I'd really like to do that someday.
It's fun. Cool. So we also have a question from Chris saying, are you saying serpentine is a mineral? If so, where are the crystals?
Ooh, great question. Sometimes crystals don't look like what we think of as crystals. So in that piece of serpentine, just because it looks sort of smooth, that's a crystal. When we think about biotite, right, that black flaky stuff in the granite, each one of those, like that flaky piece is itself a crystal. So we often think of crystals as having, these sharp edges and looking like quartz. But when we're talking about crystals as a geologist, we're talking about anything that has this sort of fixed molecular structure to it, right? We're putting those atoms together and they're holding themselves together in a fixed, you can think of it as like a scaffolding at the atomic level. And those are the crystals we talk about. So sometimes crystals do have these sharp edges. Serpentine can sometimes grow with a really nice crystal habit, but it's usually growing in these metamorphic situations. It's deep underground, it's filling in spaces. And so it doesn't have the space to grow into a beautiful crystal with sharp edges. It's usually just filling in space.
Yeah, and so I could add to that, Graham, as well. Just that, as you said, crystals can form in many different sizes, many different shapes. And so we have, garnets that form 10-sided crystals. They look like a soccer ball. We saw last week, we had a viewer send us a picture of fluorite. So that's 8-sided. So right there, we have a lot of different sort of crystal habit is what geologists call it. And Graham, this is a question for you. Isn't the fibrousness of the serpentinite a crystal habit?
Absolutely. It's a way that when you can always look closer at a rock, right? We talked about that last week. You can look at it from afar. You can get within arm's reach of it. You can get your nose right up on the rock. And then you can even start, taking these things apart with a microscope and tweezers if you really wanted to. And so, as you zoom down, that crystal habit can look different. And in the case of serpentinite, it can be kind of fibrous or bladey, almost flaky like a mica, not quite like that, but Yeah, and that all has to do with that crystal habit and the way you're putting all those atoms together.
And speaking of serpentinite, we have a couple of submissions for IDs. So again, for everyone watching, if you have questions about rocks that you found that you want to submit a picture of, or maybe it's a formation that you're curious about, you can always submit them like on the Facebook event prior to or during the event. And so one of the submissions that we got this week was from someone who thinks that they might have found serpentinite because this was in kind of the New Almaden area of the San Jose kind of foothills, and there is definitely serpentinite around there, but he thought that it seemed to be acting differently and was wondering if it could be jade. So we've got a number of different pictures. What do you guys see here?
Oh, great. So it's got that we definitely have something in this, serpentinite jadey. It's got that, rich sort of green color. And these are always tricky questions. The jade serpentinite conundrum is a common one here in California. So when we say jade is a gem, but it usually means it's one of two minerals. One that is a type of mineral called an amphibole and is called nephrite, and one that is a pyroxene and called jadeite. And these two they're different groups of minerals. They're built off of chains. So amphiboles are sometimes fibrous, and serpentine is actually related to amphiboles in that way. But nephrite's a different sort of a beast. And then a pyroxene is a whole other mineral group. They're often dark and green colored. They're a lot more common in things like basalts. And so, Gavin, what would be the key test of determining whether it's, other than being able to put it under an electron microscope or a microprobe and look at its chemistry, how can you tell the difference in hand, or what's your best way to check out the difference?
Good question, Graham. So minerals are often identified by their hardness. This is a thing called the Mohs hardness scale. It's a way that geologists identify minerals, and we'll talk about this next week. But oftentimes, as we had mentioned before, color, really not a good identifier, right? Because serpentinite and jade can look exactly the same in color. Mm-hmm. And oftentimes we see that fibrous sort of texture in serpentinite, but not always. So that's not always a really good identifier either. So with a picture, it's really hard to say, but if we had the rock in hand, we could take a paper clip and we could try to scratch it. If it scratches with the paper clip, that means that it is softer than what jade would be. So if you take the paper clip and you scratch the surface and you wipe it off and you see actual scratches in the actual rock, it's probably serpentinite. If you take the paper clip and you scratch it and you see silver streaks, that's probably the paper clip scratching off. If you wipe off those silver streaks, you won't see that the rock was scratched or the mineral was scratched at all. And so if you scratch with a paper clip and it scratches, it's serpentinite. If it doesn't scratch, it's probably jade. But as far as identifying them from the photo, it'd be really hard for us to do because, as we said, the crystal habit for serpentinite isn't always fibrous, so it could often look a lot like jade, and it could break in these sort of almost, it looks like it's glassy the way it's breaking. Mm-hmm. So it's really hard to say either one. But if you have a paper clip, try to scratch it.
Yeah, and let us know the result. We'll be excited to hear, what the idea is next week.
Yeah, report back. Okay, so then we also had another submission recently, and this one's from Nick. And let's see, are you guys seeing this? It's great.
Yeah.
So Nick was playing in a creek with some kids, and they found some round river rocks in Aptos Creek, and they were breaking them, and they noticed that a lot of them were exhibiting something similar to what we are seeing here. So what do you guys think is going on?
Okay, so this is another tough one, but let's take a crack at this one, G. Yeah. So first of all, what we can say with pretty good confidence is that the matrix, sort of the surrounding grayish areas, is probably a mudstone. It's probably similar to the Santa Cruz mudstone, darker. And there's obviously something of interest in the middle. Whether the rock weathered around that thing is hard to say. So one guess is that this thing in the middle could be a fossil, because oftentimes fossils sort of stand out from the rest of the rock. They're oftentimes smoother than the rest of the rock. So that's one guess. You have anything to add to that, Graham?
Yeah, that oftentimes in a lot of the rocks around, Santa Cruz, there are these coastal deposits, and it's not, you actually don't have to go too far, certainly not in the Purissima or in the Santa Cruz mudstone, to find just bits of critters. And it could be, anything from a shell to a bit of bone, like fossilized bone. And so, yeah, it's, again, you can sort of suss out if it's a mudstone or a sandstone just by feeling it and how gritty it is. It's probably some sort of coastal, near coastal rock. And then, yeah, if you've got, it would be certainly something that would be awesome is if there were more pictures of some of these rocks to share. We might be able to recognize a fossil shape in there. But I often, usually when I see a sedimentary rock like this, then you see some sort of dark and peculiar, smoothish looking thing in there, I often think fossil. But one way to test would be, feel how, is it smooth and hard, or is it a little bit more goopy? Sometimes you can get, mud sort of penetrating into cracks and rocks, and they can start to be sort of weathering away. And if it's really soft and goopy, that could also be what it is.
We have a couple of thoughts in the comments too. Felicia is saying that it looks like it could be a vertebrae, and that mastodon fossils have been found in Aptos Creek.
Wow.
But so
Cool.
She sees something a little bit vertebrae about it. And then Liz is also wondering if it could be a concretion.
Yes. So this was the alternative in my mind. Could this be a concretion? Oftentimes, when you have concretions, they occur in sort of round rocks like this one. But in this case, you can't really use the roundness to say for sure because it's in a river. So river rocks are usually round anyway. The reason that in my mind I got away from concretion is because oftentimes when you break concretions apart, they have this sort of circular sort of fabric inside of them, because concretions find a nucleation point and grow around that nucleation point. In this case, it doesn't really look like that's the case because there's this irregular sort of shape in the middle, and the matrix material looks just like sediment. So that's why I think Graham and I said maybe fossil, but not the sort of concretion like we would usually think of it.
Yeah, we can't say that it's not a concretion. It's just usually we think, sometimes if we see something really round, we'll consider it as a concretion. But like Gavin said, rivers are basically like giant rock tumblers. And so everything that's in a river ends up getting tumbled and getting really smooth and pretty round. So they can often be deceptive. And I often think that river rocks are some of the hardest ones to ID because they've just been so polished and so smooth that it's hard to really pick out what the minerals are in there and what's going on. But cracking them open, that's smart work, Nick, to split those open and see what's going on inside.
Yeah, we'll see if maybe they have more picture, because since Nick said that they kept finding multiple like that. So, I mean, the odds of finding many that broke open in the same way is kind of interesting. So maybe we'll hear back from Nick next week with a little bit more details.
Awesome.
We have some other people who are agreeing that it looks kind of like a concretion, but is it around a fossil or just some other mineral? Both can happen. Kind of looks like bone, and then also said like might be chert inside.
So. Could be.
So
yeah.
Especially in these sedimentary environments, right? You can be moving all sorts of things around and they could find their way into it. So definitely possible.
Yeah. And speaking of that mastodon in Aptos Creek, we have that mastodon at the museum. So once we open back up again, people can come visit our mastodon skull that was found in Aptos Creek in 1980. So lots of wonderful phenomena that happen around here in Santa Cruz. Exciting stuff. Well, I think that's a good place to maybe end it. So I hope that people continue to send in their pictures for us to ID. Do you have any parting words, Gavin and Graham?
Just thanks for tuning in. Are we going to start dancing again?
Yeah, we'll do like a little send-off dance party. So everyone at home, you know, like move along with us. And we'll see you next week. We're going to be talking about what again? What are we talking about next week?
Identifying rocks and how you guys can too.
Okay, that's what we're going to do. Thanks for joining us, guys.